Hello, everyone. Good morning and welcome to the talk. And my name is Kwok Sin An from the University of Leicester, and I'm doing my PhD in my final year. And I'm almost finished now, so I will present one of the chapters in my PhD thesis. So the title of this paper is called Equity Risk Premium Prediction, the Role of Technical Trading with Mixed Frequency Models. So first of all, let's talk about what is technical analysis. Technical analysis is the study of market trends and relies on the recognition of the price patterns in an attempt to predict future security prices. So here are some of the popular technical indicators, like the moving average crossover rules, momentum rules, filter rules, and etc. So as an example, here we present a moving average trading strategy. So as you can see, this is an Hang Seng index, which is the stock market index for the Hong Kong market. So in here, a trading signal is generated when a short-run moving average, so the red line, is above the long-run moving average, then a buy signal is generated. So for the momentum strategies, it's trading as follows. If the current price is above the price level, say for 3 months ago, then it's a buy signal, otherwise it's a sell signals. So it's just very simple technical trading strategy. So the motivation of this paper is, as we can see, there were more and more data in the markets, and there were more high frequency data available in the market. So we want to test whether higher frequencies data will be useful for technical traders to forecast the monthly equity risk premium. So most of the existing studies only uses monthly data to forecast monthly equity risk premium. We wanted to see if there is any actual values when we consider higher frequency data, such as daily data and weekly data. For these data, we can have a longer time series. So the research objective is to test the mixed frequency models with technical tradings. And we want to see if those forecasts could actually enhance the forecasting accuracy of monthly equity risk premium. So let's look at the literature first. So as you can see, many of the existing literatures has actually tested higher frequency data on forecasting lower frequency like consumer confidence index. And as you can see, we can see higher frequency like tick data, 5 minutes data and 10 minutes data, and actually improve weekly realized volatility forecasts with the mixed data sampling regression models. And we also see some mixed results as well. So when we forecast monthly real price of oil with daily or weekly predictors, is actually high frequency data did not improve the forecasting accuracy. So in this case, we want to see whether technical tradings can add value in forecasting monthly equity risk premium. So let's see, we'll just look at two very simple predictors. So the first predictor is the technical trading with the moving average rule, like I've presented in the first few slides. And so a buy signal is generated when the short-run moving average is above the long-run moving average. And here is another presentation of the momentum trading rules. So the parameters were used according to the literature. So for the MA1 and 9, it actually stands for the moving average of 1 month and 9 months. So the short-run moving average is 1 month, and then the long-run moving average is 9 months. So when the short-run moving average is above the long-run moving average, then there is a buy signal. Otherwise, it will be a sell signal. So we will classify it using 1 and 0 in this case. So for the momentum trading rules, we also have a set of parameters like 3 months, 6 months, and 9 months, 12 months. So we have collected the data, the closing prices from here for the S&P 500 between the sampling period of 1950s to 2019. So by assuming there are 20 trading days, or there is 4 trading weeks in a month, we can actually compute the moving average indicators and compare them. As you can see, when there's 20 trading days in a month and 4 trading days in a week, so there will be 20 signals in a month and 4 trading signals in a week, and 1 trading signal for the monthly indicators. So we can actually compare those indicators. So in the following, you can see this graph is generated with moving average with daily data, so it's more high frequency data. So you can see many spikes in the graphs. And this is a moving average of 2 months and 9 months. And if we expand it, so 2 months is actually equals to 40 trading days, and 9 months is actually equals to 180 trading days. So we can actually compare these technical indicators directly and see if there is any value in the high frequency data than the low frequency data. So if we compare it to the weekly data, so there's 2 months, which is equals to 8 weeks, and 9 months is equal to 36 weeks. So you can see, comparing to the graphs, the resolution of the graphs is actually getting less clear, or there's more spikes for the high frequency data as you expect. And this graph is actually plotted with monthly data. So we here want to test the value of high frequency data, and we want to align it with the low frequency data. So one of the conventional way to compare technical indicators and different frequency is to, one of the conventional way is to align it using an equal weight scheme. So just take an average of those technical indicators for a month and then compare it directly. In the other case, we can apply the MADIS model, which is the mixed data sampling model. And we can actually use what we follow the literature, and then we can use the Ullmann-like polynomial weighting function in here. So if we plot it out, then we can see it more clearly. So the aggregation horizons, we will like there's 20 trading days in a month. So by following the exponential Ullmann-like polynomials, we will weight higher towards the end of the time series. So the later days of the month, we will actually assign a higher weight to those indicators than the indicators in the earlier months. So we will align the high frequency data to a low frequency data. So as an example in here, so we have actually got this is a hypothetical example in here. So if we generated daily trading signals for January in 2022, as you can see, we have actually like 20 something trading signals for daily technical indicators, while as if we transform it to weekly data, we will only got 4 trading signals. And for the monthly trading signals, the end of monthly trading signals we only got 1. So we want to actually compare if there is any values in the high frequency data compared to the low frequency data. So for the Ullmann-like polynomial in here, so this is the graphical presentation. So we will actually assign a much higher weight. So like 27% of the weights we will assign it to the end of the month in here. And we will give a less weight to the trading signals in the earlier of the months. The reason why we skip those trading signals in the earlier of months, because some of the trading months, we only have 15 trading days. So to avoid the model using data beyond the months, so we will only allow trading signals towards the end of the month, like the last 15 of them. So in this case, we will not using data beyond the month. So for the weekly trading signals, we will apply the Ullmann like polynomials. So we will assign 33% to the trading signals at the end of the month, and then a much lower weight for the early of the month. So we put, after we aligned those indicators, we will compare it in the following regression to forecast the one step ahead monthly equity risk premium. So this psi A is one of the 10 aggregated technical indicators when A denotes the frequency of concerns. So we will compare it to daily, weekly, or monthly. And then we want the following just ordinary least square regression. And following the literature, we will compare it to the benchmark model, which is the historical average forecast. The historical average forecast is just the average of the monthly equity risk premium. And here is a sample of the forecast of the historical average forecast and the actual monthly equity risk premium. And one of the models is the moving average with 2 months and 9 months. So for the example period, we will use between 1950s to 1965. Yeah. So for the out of sample forecasting periods, it will be between 1966 to 2019. So the next step is to calculate the out of sample R squares. So it's one way of presenting how good is the model in forecasting monthly equity risk premium. So for the numerators, we will have the actual risk premium, and then this is the forecast of the forecast of concern. And for the denominator will be the actual minus the historical average forecast. By taking the square of it, we can actually see how good is the model. So we will import the Clark and West statistics to test the hypothesis whether this out of sample R square is less than zero, less than or equal to 0 or greater than 0. So to see if each of the forecasting models can outperform the historical average forecast. And by plotting it out the results, we can actually see by varying the aggregation horizons. So for the one in here is the last trading signal of the month. So if we just repeat the models by adding more data in each month, so we will allow one daily data in the model, and we will add it up to 15 of them. So we want to see if we consider more and more high frequency data, is there any value of it? So as an example of it, we will also apply a 3 weighting scheme. So one of the classic weighting scheme is the flat weight indicators. So in which case we will just assign a equal weight to each of the high frequency daily data and align it to a low frequency. And the purple line, the purple solid line here is the monthly indicators. So we can actually see there is some value for the day. So this is the moving average with daily data, and this is one is with weekly data. So we can see for the daily data, we can actually see some values in outperforming the low frequency data, whereas for the weekly data, we cannot see any additional values of it. So if we go through all the graphs in here to see each trading strategy with different parameters, we can generally see that there is not much value in high frequency data compared with the monthly data for the moving average rule. As you can see, it's actually underperforming the monthly indicator. So whereas for the momentum trading rules, we can see there is a much higher value in high frequency data when compared to the monthly low frequency data. It's the same applies for the daily data and the weekly data as well. So you can see it's actually outperforming, and it's only underperformed for the momentum 12 months strategy. Otherwise, overall is the momentum trading strategy, the high frequency data is actually adding more values to the momentum trading strategy, but not the moving average strategy. So here is the principal components of those indicators, but aligning those 10 aggregated technical indicators of concerns. So we can actually see there is some value when we consider the end of the month's trading signals. And when we add more and more signals, the forecasting accuracy will actually decrease. So there is no clear evidence of high frequency data for moving average strategy, whereas there's more value to it for the momentum trading strategies. So in the asset allocations, we will test the following models. So here is the assets allocation result by comparing it to the monthly moving average strategy with the daily strategy. So you can see there is only a minimal difference as you would expect, because the two trading strategy are so closely related to each other. So there, as a result, the assets allocation will be very similar. So we want to see if there is any value in such high frequency data. So we test the portfolio result. So we calculate the certainty equivalent return of the portfolios. And then we want to see if there is any actual value of it. So in assets allocation perspective, we can see there are some values of high frequency data when we consider the end of the month. But when we add more data to it, it's actually getting worse of it. So here are the conclusions. So high frequency data can actually add value to the momentum trading strategies, and we can see there is a certainty equivalent return gains between 0.15% to 1.54%. And the end of month indicators, irrelevant of month, daily or weekly, there is which contains more information in forecasting equity risk premium. So it's actually the fast decaying weights will actually outperform the other weighting scheme, as you will see, because there is more relevant forecasting information contained at the end of the month. And we have tested those results with the consideration of transaction costs of 0.5 basis point, and the results are robust in superior analysis and with different choice of risk preference. And here's the presentation. And I hope it's clear. Yeah. Thank you. Yeah.
Okay, thank you. Thank you for your presentation. I'm a practitioner. I'm actually doing algorithmic trading project. And for me, hearing about strategies and then just risk, it like a bit weird, because it should be like P&L together with risk. This is when you say the added value for the algorithmic trading, it means that we should profit more. So why don't you apply any P&L analysis here together with risk?
So sorry, I'm not hearing quite well. So what do you mean? Like,
I mean,
yeah.
Talking about trading,
Yes.
and then money is the goal.
Yes.
And you can't talk about risk like in the year. You have talked about money together with risk. So
Yeah.
less money, higher risk, or more money, less risk, like this.
Yeah. So.
About risk,
Yeah. So because we are talking about forecasting accuracy, so I might not make clear about, because we have actually done an asset allocation analysis in here. So for the forecasting exercise in the earlier slides, so in here we actually generated and forecast with technical indicators at different frequency, and we can actually use this ORS forecast to make a mean variance portfolio weight prediction. So in here, we actually we can generate a weight for the portfolios, and we have test the profitability of those portfolio in terms of certainty equivalent return, which is calculated as follows. So the average return of the portfolio and minus, so this is the risk preference, and these are the standard deviation of the portfolio. So we have actually used the certainty equivalent return as a measure of performance of those indicators. Yes. So here are the performance of the certainty equivalent return gain when we compare those indicators. So we have actually done it. Yeah. Any questions? Thank you very much for the questions. Thank you. Yes. Yeah.
And when is your graduation?
September.
September.
Yes. This one, right?
Yeah,
thank you very much.
PhD thesis in September this year, so we wish him all good luck.
Thank you very much.
I think it's F5, no? Oh, that's your presentation? Yeah, it's
Can you see?
yeah. Never do this. You got the next slide. Is that right? Okay, good. Oh, thank you very much and good afternoon. Welcome to this session. We have to stick to the timetable because people will see this at home. Well, in fact, one person at this right moment, but it will also be stored. This is the third year after my first visit to a ISF. That was in 1992 in Wellington, New Zealand. And I'm very happy to be here again in Oxford for this conference. And I thank the organizers for putting this conference together. And given the state of most of all, when I left this yesterday afternoon or evening at the dinner, I think I'm only one of the few still having a voice. Yes, I think that's correct. What I will do is a very short presentation on what I called an introduction to time varying lag autoregression. And there is not so much new in this, because some of you might remember certain highbrow nonlinear models that encompass these. And that's particularly one of the reasons why I do this, because one of the things that I heard yesterday in the presentation of Shari Debat, that she says, if a model is never used, it's useless. And well, I think that's correct. So some of the very highbrow nonlinear time series models are very elegant and very beautiful, but nobody uses them. And the reason for those, I can perhaps show you later on in some of my statements. And the other thing is, in another session on judgmental adjustment, and it's also my personal experience working on judgmental adjustment, is whatever type of model people have used, people will always try to adjust the forecast. I was also involved in a Central Planning Bureau exercise. It was published in this journal here, where they have this 2,500 equation model that they spend with 10 people estimating and trying out and tuning. And then the final results end up at a desk of a couple of experts, and they just modify by hand the ultimate forecast. So the lesson is, the more complicated the model does not guarantee that people will not adjust it. But what we do know from the adjustment literature is that people who do not understand the model will definitely try to adjust it. So that's one of the reasons that I thought, let's try to do something simple to begin with. It will be very simple. I hope that all of you will immediately understand it. Extensions are plenty. You can come up with, as along I talk, you can come up with your own ideas of extensions. So that's all rather easy. But I want to go back to the very basics. And this is what I'm doing next. I will just propose a very simple autoregressive model. And I should say the motivation for this comes from my recent work with two types of colleagues. One are historians, and historians don't have big data. They sometimes have no data at all. And once they have data, they have gaps. You know, they lack the 16th century. They do have 15th, they do have the 17th and 18th, but no data on the 16th. So what then we do? And typically in that area, they start to interpolate. But that's very bad practice if you do that, because you increase and in fact introduce autocorrelation that's not there. So if you want to correlate two variables with missings, and the missings are being interpolated, you get spurious regressions. And the other thing is that the people in business that I sometimes consult, they have these zero-valued sales data. The shop is closed. There is a strike. There is no driver. Yesterday, I heard in the hotel that they had problems with deliveries because there was no driver driving the truck, getting the stuff to the hotel. So that can happen. The zero value is not something to dismiss. And what people sometimes in practice do is say, let's aggregate over time. If we have zeros at the daily level, let's move to the weeks. But that comes with very unpleasant surprises because you can't draw inference on the daily data based on weekly models. Well, you can in certain very specific situations with hypotheses and some assumptions, but in general, it's very difficult to do. Now, one strategy could be then is just to change the model and to see if you can cope with some missings or some zeros without dismissing them. And one idea could be to have different lag structures. So sometimes it's lags 1, sometimes it's lag 4, sometimes 3, sometimes 10. For the ease of illustration today, I will just go for 1 and 2. And the idea is reasonably clear. So I'm not going to vary the lag structure, I'm going to vary the lags. So the variable will become something like not yt minus 1, but yt minus lag of t. And that can be 1 or 2 or 3 or 5. I will discuss the standard routine of representation, autocorrelation, specification, inference, just to see if it works. Because if you cannot compute moments of these things, or you cannot compute autocorrelations, then it's not very useful for practical purposes. So this is just a basic check. Of course, if models become more complicated, things might become more complicated, but as we will see, inference is rather simple. And in the end, it can also be viewed as a little bit of a combination of models that you have sometimes a forecast 1 step ahead, sometimes 2 steps ahead. So it's a combination of forecasts, which in the end we will see can also reduce forecast error variance, which is what usually happens with forecast combinations. So I try to mix the whole things in a row, and I try to illustrate this because this is a session on econometrics, so it's not on forecasting, so I will just go for FIT and AIC and BIC, and I took inflation rates for 8 African countries. I use these data because we compiled this complete data set. It's a very big one that concerns all countries and the years 1960 to 2016, and that's complete. So what's the idea? We start with an autoregression of order 1. This is also how I teach things, and often students say, is there not more than that? Well, if you understand the order 1 case, then it typically moves on quickly to the order 2 or 3 or 4 case. And this is how we usually write it. We have a variable yt, depends on yt minus 1, parameter alpha, unknown mu, errors, standard white noise to make it simple. Moving averages are possible, but not that easy with 0 values, by the way. But we will see that later on. And a simple extension that people have considered, and there's this very good book by Jan de Gooijer, a big summary book on nonlinear time series models, is that you could move from the alpha yt minus 1 towards a function of yt minus 1 and parameters. And that function can be anything. Yeah, so it's you can have jumps, you have thresholds, changing regimes, Granger and terrestrial. I have this some survey book on that. And there are tons of nonlinear time series models. If you go to the regular issues of the Journal of Time Series Analysis, in every new issue, there is a new model. Yeah, so that's, you may wonder why, but at least there is one. Now, what happens in practice that even though many of those elegant nonlinear time series models exist, they're not often used. In fact, I've been to 14 lectures, 14 sessions this conference, and I haven't seen the word nonlinear at all. That's all machine learning, which if you spell it out, it is some way of nonlinear things, but then a whole bunch of linear steps in a sequence or together. But the word nonlinear is not there. If you go 20 years back in time, it was in half of the sessions. The same, by the way, about unit roots. There is no unit root keyword here in the index. And 20 years ago, it was the only thing that we talked about. But that's something different. Well, we see that for many of those nonlinear time series models, and that's the book of de Gooijer is very instructive, it's very difficult to establish, for example, stationarity. So how can we show and see that the data, as you generate the data from a model like that, are stationary? It's very complicated sometimes to prove, and it's sometimes not even establishable, and it's even worse sometimes for certain parameter regions, it's not stationary, and for others it is. But if you have to estimate these things, you have to assume stationarity. So this is a bit of a chicken and egg kind of problem. Well, you know, maybe you have estimated your Garch 1.1 model once, where the sum of the terms add up to 1.2. And you say, well, that should not be possible because the theory says it's stationary if it's smaller than 1. But you can get it. Sometimes these models face very complicated estimation routines. And even worse, although it's very elegant statistically, some of those have unidentified parameters under the null hypothesis. So for example, a threshold disappears if the data are linear and there is no threshold. So then there is a very complicated statistical analysis to be used, the Davis problem it's called. And therefore I decided to propose a very simplified version of models that were introduced in Tong in 1978 and Lawrence and Lewis in 1980. I checked the recent quotes to these studies and they seem to reduce. And maybe that's one of the reasons why this. So what I'm just in essence doing is assuming the following first order, if you like, autoregression, where the t-1 is replaced by t minus lag t. And lag t can be 1 or 2, or and lag t is a dummy, it's either 1 or 2 or 3. White noise still for epsilon t, mu is still this constant, and alpha is still assumed to be absolutely smaller than 1. The nice thing about this framework is that with this, by construction, this stationarity is very easy to verify because it holds for t-1 and the same restriction holds for t-2. So stationarity is easily established. I got this submitted somewhere, I forgot where, and the referee said, can you also introduce that lag t is not a dummy, but a Markov chain or something? Of course, but why would we? You can also do it in different ways to find that lag structure. Of course, you can make it functions of additional variables. You can have a smooth function in it that goes smoothly from 1 to 2, whatever. That's perhaps making things more fancy, but also not more easy to apply in practice. It's always good, and I also teach my students this, that if you create something new, generate data from it and to see if they look like reasonable. Is this the kind of data that we see in practice? Now here is a data from an autoregression of order 1 and a time varying lag autoregression where the lags are 1, 2, 1, 2, 1, 2, parameter at 0.9, and the blue line is the regular AR1 and the red or orange line, I think it is, it's a time varying lag autoregression. So they look similar, but not, but maybe there's some more variability, but at first sight, eyeballing, it's difficult to distinguish them. Well, matters become a little bit different if you have only a period where the lag starts to be 2. So first that is lag 1, then it's lag 2, and then it's lag 1 again. Yeah, then we see something, and this is also how I come up with my application for African data, as we will see because I have pictures of those data. That's six-sawtooth in the middle. So that pattern that goes up and down in the middle is reflecting that change of this autoregressive structure. And we will see that for inflation rates in Africa very soon and quite often. Unlike in Western countries, inflation in Africa can go up and down from 2 to 40 and back to 2 just in 1 or 2 years. Yeah, that's how it goes. Unconditional moments are very simple to derive. They're the same because it's a yt-1 and yt-2. So these are the same. Unconditional variance is the same. Autocorrelation is slightly more tedious because it depends on how this lag structure works. So 1, 1, 1, 2, the changes, there's a change. So you can have 4 situations, lag 1, 1, lag 2, 2, lag 1 and 2, and 2 and 1. And that has a certain amount of observations in it, and you need those to compute the first order or second order autocorrelation. Just as an illustration, the first order autocorrelation of the process that we have seen in the first graph looks like this. Now, we can go on like Box and Jenkins did, and their followers to derive for any kind of ARMA process their autocorrelation functions, but again, it seems that these are rarely used. But at least they exist. And if we take some numerical values. So the first case that we had, we see that the first order autocorrelation is alpha squared plus alpha divided by 2. And that means that if alpha is 0.9, the autocorrelation is slightly less than that 0.855. In this case, this alternating case, so 1, 2, 1, 2. So that's the first picture. The second order is the same as the first order. And if we move on to the fourth and the third, they also have the same numbers and have the same kind of structure as we're familiar with in the autoregression models. Parameter estimation is very simple. You just include, if you like, a dummy variable. You can use I use often eViews. You just click in y minus lag parentheses, and then hop, everything runs. But otherwise, you use dummy variables and you estimate this simply by ordinary least squares. So the only thing that we have to arrive at is how do we get the value of lag? So when do we know it's 1? When do we know it's 2, or some other term? Now, this was firmly refuted by one of the reviewers that I said, well, let's try. Let's try and run autoregressive of order 1, one of autoregression of order 2, so the lag of 2, and see where the residuals are smallest and go for that one. Now, if I look at all the machine learning studies that we see here in this conference, people make multiple millions of decisions on tuning parameters. So I thought, well, this might perhaps work as well. But if we are the strict followers of firm statistics, apparently it's not. So maybe I should sell this as a machine learning piece, and then people say, oh, that's good. You could try out various settings and then choose the best one. So you take for the estimated residuals, and this is fairly simple to do. Forecasting can be done quite trivially as well. You just plug in the future values and you see what do we know at time t. So when it's the forecast at time t for t+1 is the simple autoregressive term as you are familiar with. And when it's 2, it's just leapfrogging that one period. Yeah, and that means, but of course, at the horizon, at the origin, we are not certain whether it's 1 or 2. What seems to be the best is to take the average forecast. So here is this forecast. If we combine it and we sum the forecast, we get the forecast error equal to epsilon t+1. So the regular one that we should expect in regular time series. So this is also what people do when you have Markov switching models. If you have 1 or 2 steps ahead, you do not exactly are firmly certain about the current state of affairs. So let's take 2 forecasts and combine them. Now, if we do that here, we get the regular outcome. If we go to 2 steps ahead and we take that combination, then the nice thing is that we see that the forecast error, so that's halfway at the bottom, is not including alpha epsilon t+1, but a half of alpha epsilon t-1. And this is because we leapfrog that t-1 stage if we have 2 lags. Yeah, so we have this smaller combined forecast variance, which is a result that associates with the forecast combination literature. Yeah, so this is how that works. Now, misspecification, when can it happen? There are 2 ways, of course. If the AR is true or you fit a TV, a time varying lag, then you get autocorrelation in the estimated residuals. So this is one way to diagnose it. And it's the other way around. If your time varying lag structure is true, but you fit an AR, you get arch effects. And that was one thing you could see from that pattern in the data. You will miss out these observations, and that will be squared, giving you arch. Yeah, so the diagnostic seems to be not that difficult to look at. Now let's have a look at some illustration. I have 8 countries. I do have all the 52. We spent quite some time together with a colleague of mine, Eva Janssens, to impute based on a large database the missing inflation rates for certain countries in certain periods. Think of Rwanda in 1994, 1995. There were no data by then. So we were able to impute them. They have been used in 1 or 2 other studies. And here you see, look at the Burkina Faso period, the sample. I'm not sure what I'm pointing at the wrong thing, or the right thing. So it goes up to 20, then it goes down to -7, and then goes up to 30, just in 3 years. Well, trust me, no linear time series model can handle that. And it will all tell you these are outliers. While they go on, there are many outliers. So if you go for the outlier selection here, you find that half of the data are outliers. I'm not saying that perhaps some of the observations might not be correctly measured. Not all African countries have a well-developed statistical reporting system, but this is the data from the World Bank. So this is what we have. Here is some other data. Look at Sudan, 120% inflation is possible, and the year after it's just 0. So that's the kind of data that we're looking at. Now, this is the detected lag structure using the method that I just used. You see 2, 1, and that it goes up and down. You might even want to discuss if there are commonalities across these lag structures. I'm not sure whether that's interesting, but maybe you can do. And here is just some AIC values and BIC values. The bottom row is always the time varying one, and it has the lowest values of those criteria for all countries. I just report 2, but that's for all countries. Of course, I did some selection. Yes, so I selected this. So I should perhaps correct my AICs and BICs for the fact that I searched over the lag structure, but I'm not sure yet how to do this. Well, this brings me to an end. It's also 12:41. Extensions are possible. In fact, I have already done a few things because especially the historians like this. Because what historians sometimes want to do is to compute impulse response functions across 2 variables with all kinds of gaps. And that's think of the 16th and 17th century, where they sometimes have missing periods of data due to wars, for example. Yeah? So they like these kind of extensions with having an X variable in it. And you can have extended autoregressions. Of course, we can refine the selection process because now it's just taking the error terms, but you can make it a function of the absolute values and different functions, whatever you like. You can take some certain thresholds, but that's for further work. And because of the time, I think it's good for me to stop here. Thank you. For the people at home and for later,
so in the linear time series, we use ACF to make some identification issues, right? Can you think of some descriptive tools like autocorrelation function, but it's not lag varying, but time varying kind of function?
Yeah.
That would be useful.
That would be certainly useful. I must say that my impression is that if people look at autocorrelation functions or partial autocorrelation functions, they typically check the first few. So it would be helpful to have some refinement for that first few of those. Yes, good point.
Yeah. Thank you.
Anyone?
Just really quickly, are you concerned about it changing very quickly? So I looked at the last graph you had where it's going lag 1, lag 2, lag 1, lag 2 very, very quickly. And that seems to me like it's overfitting. It's changing rapidly.
Yeah, well, I guess this is my choice of those variables. If I would have chosen US inflation or something, it would be just a few points. A few times that it would be better to take lag 2. But this also shows perhaps the vulnerability of those statistics in African countries. I must say, I just, when I was preparing my lecture, I just looked at the first time series that I could think of and then hopped. So I didn't search for the best possible illustrations.
So it's really fascinating proposal about looking at time varying lags like this. And interestingly, it's actually it's a specific algorithmic implementation of a special case of what's known as multiplicative indicator saturation, which was proposed about a decade ago, where you allow slope coefficients to change. Mm-hmm. And of course, here you're having the special case where the slope coefficient on lag 1 is either alpha or 0, and the slope coefficient on lag 2 is 0 or alpha. And so that also, and there's a statistical basis for all of this now too, through the work that Soren, Johansson, and others have done in terms, and Benton, of course. So it does suggest some extensions of what you might want to do here. And one, of course, is not to be imposing that the alpha on lag 1 and the alpha on lag 2 are the same. And furthermore, to be able to actually allow the intercept to vary across these different periods. And Jennifer Castle was talking yesterday about an actual example with climate change, where those sorts of switches could be actually quite important because they can change the equilibrium mean. And the graphs you have here really do suggest changes in equilibrium mean.
Now this goes back to I think it was in stochastic processes and applications, Peter Robinson paper in 1977 on a general version of an autoregressive model where you can have the time to be short or small depending on what you do. Then you have heteroscedastic errors. And this is the thing that we actually use now in some of our historical studies, that you make so the parameter for t-1 is alpha, and for t-3 is alpha to the power 3. And then you can also switch that over time. And then, of course, you can also make that alpha 3 being alpha or beta. Yeah, these are all things, these are all possible. Yeah, sure. Just for all the people who just came in, this is the last lecture in the session. So I'm not sure if you're waiting for someone.
Thank you for the presentation. And for the parameter selection process, I was wondering, is it estimated recursively, which means from day 1 to the end of this sampling period, or does it come with a rolling windows?
This is just with the full sample. But
just with the full samples?
Yes, but we can do this for rolling samples if you like, or recursive, no problem.
Yes,
it's just ordinarily squares.
So it all fits like, so it performs as well as from the full samples recursively and do the same for the rolling window.
Oh,
do we have the same results?
A good point. I didn't check that, but that's interesting to do. Yeah.
Yeah, thank you very much.
Yeah. Oh, sorry, I'm the chair. Any other questions? Then if not, thank you for coming.